Assalamualaikum and good afternoon. My name is Muhammad Hazim bin Zul Azli. My student ID is 2023698886. Today, I will present my final year project titled called Development of a Secure AES-based File Encryption System with Improved Key Management. This project was supervised by Dr. Muhammad Yusof bin Darus. Nowadays, many important documents, images, reports, and PDF files are stored digitally. Although digital storage is convenient, these files may be exposed to unauthorized access, theft, accidental disclosure, or modification. Encryption protects this information by converting readable data, known as plain text, into unreadable ciphertext. The ciphertext can only be restored using the correct encryption key. AES was selected for this project because it provides strong security and efficient performance. Therefore, this project develops a local desktop application that uses AES-256 encryption together with improved key management and file integrity verification. Now, let's talk about the background of the study. AES is a well-established encryption standard used to protect digital information. AES-256 provides a very large key space while maintaining efficient file processing. However, the security of an AES system does not depend only on the algorithm. It also depends on how the encryption keys are generated, stored, and accessed. If keys are stored in plain text, reused across several files, or protected using weak passwords, the encrypted files may still be compromised. Another issue is that AES-CBC provides confidentiality but does not automatically detect whether the encrypted file has been altered. Therefore, this project combines confidentiality, integrity verification, and secure key storage in one local application. Now we move on to the objective of the study. This project has three objectives. The first objective is to design a secure key management mechanism that supports cryptographically secure key generation, encrypted storage, password authentication, controlled key retrieval, and key lifecycle monitoring. The second objective is to develop a secure AES-based file encryption system with improved key management and file integrity verification. The third objective is to evaluate the system in terms of functionality, performance, resource usage, and security. These objectives cover both the technical cryptographic implementation and the practical operation of the completed system. Now let's talk about the problem statement. Many basic AES file encryption applications focus mainly on converting plain text into ciphertext while paying limited attention to key security. For example, encryption keys may be stored in plain text, reused for multiple files, or protected using weak passwords. If an attacker obtains the key, the protected file can be decrypted without breaking the AES algorithm. AES-CBC also does not automatically determine whether the encrypted content has been modified before decryption. Therefore, there is a need for a secure and user-friendly application that protects both the encrypted files and their corresponding keys. My proposed solution combines AES-256-CBC, HMAX SHA-256, unique keys and IVs, and encrypted password-protected local key vault. This project provides several important benefits. First, AES-256-CBC protects file confidentiality by preventing unauthorized users from reading the original content. Second, HMAC SHA-256 verifies file integrity and prevents modified encrypted files from being decrypted. Third, encryption keys are encrypted and authenticated before being stored in the local vault, reducing the risk of plaintext key exposure. The system also provides access control functions such as password validation, field attempt monitoring, cooldown protection, and vault locking. In terms of reliability, SHA-256 comparison confirms that restored files match the original files. The graphical interface also makes the system easier to use for people without advanced knowledge of cryptography. During the literature review, I examined previous studies related to AES encryption, cloud security, dynamic key generation, password-based protection, and key management. The studies generally agreed that AES provides strong confidentiality and efficient performance. However, they also showed that poor key generation and storage may weaken an otherwise secure implementation. Some researchers proposed dynamic AES keys, hybrid cryptography, blockchain-based key management, and chaotic key generation. These studies influenced my decision to generate a separate key for each file and to protect the keys inside an encrypted vault. The literature also supported that the need for integrity verification because encryption alone does not always detect modified ciphertext. Based on the literature review, I identified several gaps in existing systems. Some systems encrypt files but do not securely protect their encryption keys. Simple AES-CBC applications may also lack integrity verification. Other systems store keys in plain text or depend only on weak passwords. Some also reuse the same key across several files and provide no fail attempt monitoring, automatic locking, or integrated testing. To address these gaps, my proposed system includes AES-256 CBC encryption, HMAC SHA-256 verification, a unique AES key, and IV for every operation, PBKDF2 base vault protection, encrypted and authenticated key records, password strength validation, vault locking, cooldown protection, key expiry monitoring, and an integrated testing suite. Now, let's move on to the methodology. The waterfall model was used as the development methodology for this project. The first stage was planning, where I identified the main security problems and defined the objectives and scope. The second stage was requirement analysis, where I identified the necessary system functions, security requirements, software, and hardware. During the design stage, I prepared the architecture, system workflow, key vault structure, and graphical interface. The development stage involved coding and integrating the Python modules. After that, functional, performance, resource, and security testing were conducted. Finally, the results and system development process were documented in the thesis. This slide shows the development environment and the overall system workflow. The application was developed using Python 3. PyCryptodome was used for AES encryption, HMAC verification, hashing, padding, and cryptographically secure random generation. Tkinter was used to develop the graphical interface, while JSON was used as the local key vault format. The psutil library was used to measure CPU and memory consumption, and Visual Studio Code was used for development and debugging. For the system workflow, the process begins when the user creates or unlocks the key vault. The user then selects a file. The system generates a unique 256-bit AES key and 16-byte initialization vector. The file is encrypted using AES-256 CBC, and HMAC SHA-256 is generated over the IV and ciphertext. The encrypted file is saved with the .denc extension, while the AES key is encrypted and stored inside the vault. During integrity checking or decryption, the system retrieves the correct key and verifies the HMAC. If the file is valid, the original content is restored. If verification fails, the system rejects the file because possible tampering has been detected. The security design is divided into file protection and vault protection. For file protection, a unique 256-bit AES key and 16-byte IV are generated for every encryption operation. AES-256 CBC protects the confidentiality of the file, while HMAC SHA-256 authenticates the IV and ciphertext. The system verifies the HMAC before decryption and stops the operation if verification fails. For vault protection, PBKDF2 HMAC SHA-256 derives the vault protection keys from the user's password. It uses a random sort and 100,000 iterations to increase the computational cost of password guessing. The AES file keys are encrypted before being stored, and HMAC SHA-256 protects each key record against modification. The vault also includes passwords authentication, field attempt monitoring, cooldown protection, and locking functions. This slide begins the project demonstration. When the application is launched for the first time, the user is required to create a secure vault password. The system checks the password strength and requires confirmation before creating the vault. When the vault already exists, the user must enter the correct password to unlock it. After successful authentication, the main interface is displayed. From the main interface, the user can select a file, encrypt or decrypt it, check its integrity, view metadata, encrypt multiple files, search stored keys, delete key records, change the vault password, and run system tests. The interface also contains an activity log that records completed operations and errors without revealing passwords or raw encryption keys. This slide shows three important system operations. The first screenshot shows successful encryption. After the user selects a file and clicks the encryption button, the system generates a new AES key and IV, encrypts the file, and saves the result using the .enz extension. The generated key is then protected and stored in the vault. The second screenshot shows successful integrity verification. The system recalculates HMAC SHA-256 and compares it with the HMAC stored in the encrypted file. The result confirms that the file has not been modified since encryption. The third screenshot shows the metadata viewer. It displays information such as the file name, file type, encrypted size, encrypted algorithm, IV size, HMAC size, key creation date, expiry date, and current key status. The metadata can be viewed without decrypting the original content. This slide shows the integrated security test interface. The user selects a test file and runs the automated security test. The system then evaluates several security properties of the application. The tests include wrong key rejection, HMAC tamper detection, unauthorized vault access, unique IV generation, ciphertext unreadability, and valid file round-trip integrity. The results are displayed directly inside the testing interface. This allows the user to verify that the system correctly rejects invalid keys, detects modified encrypted files, and restores valid files accurately. In my final test, all 6 security tests passed successfully. Now, let's move on to the testing and evaluation. The system we evaluated using 4 main testing categories. Functional testing examine vault creation, password authentication, file encryption, decryption, integrity verification, metadata viewing, batch processing, and key management functions. Performance testing measured key generation, encryption and decryption times using files of different sizes. Resource testing measured CPU and memory usage using the Pisutil library. Security testing consisted of 6 test cases: wrong key rejection, HMAC tamper detection, unauthorized vault access, unique IV generation, ciphertext unreadability, and valid file HMAC with round-trip integrity. These tests were conducted to determine whether the system satisfied its functional and security requirements. The system successfully encrypted and decrypted different file types using AES-256CBC. After decryption, SHA-256 hashes were used to compare the restored files with the original files. Matching hash values confirmed that the files were restored correctly without changes to their content. HMAC SHA-256 successfully detected modifications to encrypted files and prevented tampered files from being decrypted. Testing also confirmed that a unique AES key and IV were generated for every encryption operation. The system was also able to identify active and simulated expired key records correctly. For the security test, 6 out of 6 tests passed. The results demonstrate that using AES alone is not sufficient for complete file protection. AES-256CBC successfully provided confidentiality, but HMAC SHA-256 was necessary to verify that the IV and ciphertext had not been altered before decryption. Encrypted vault records reduce the risk of exposing file keys in plain text. PBKDF2 also strengthened password protection by applying a random solve and repeated hashing operations. The graphical interface made the system more practical because users could perform encryption, decryption, integrity verification, and key management without manually handling cryptographic keys. However, the system is still a local, single-user prototype. It cannot completely protect against a compromised operating system, key logging malware, memory attacks, or hardware-level threats. In conclusion, a secure AES-based file encryption system was successfully developed as a local Windows desktop application. The completed system integrates AES-256 CPC encryption, HMAC SHA-256 integrity verification, cryptographically secure per-file key generation, and encrypted password-protected key storage. It also includes batch encryption, metadata viewing, vault locking, password changing, key expiry monitoring, and integrated testing functions. The first objective was achieved through the development of the secure key management mechanism. The second objective was achieved through the implementation of file encryption and integrity verification. The third objective was achieved through functional, performance, resource, and security evaluation. Overall, the project demonstrates that file protection requires strong encryption together with integrity verification and secure key management. There are several improvements that may be implemented in future work. First, AES GCM may be used to combine encryption and authentication in one mode. Second, large files may be processed in smaller chunks to reduce memory consumption. Automatic key rotation and enforced key expiration may also improve life cycle management. The system may be expanded to support multiple users with separate vaults and permissions. Hardware backed storage, such as TPM or a hardware security module, may provide stronger key protection. Future versions may also support Windows, Linux, and Mac OS, include encrypted cloud backup, and undergo formal penetration and usability testing. That concludes my presentation on the development of a secure AES-based file encryption system with improved key management. Thank you for your time and attention. I would also like to thank my supervisor, Dr. Muhammad Yusuf bin Darus, for his guidance throughout this project.